introduction. So she's from University of San Diego. She has been always interested in connections between graph theory and other parts of mathematics. And today she will talk about some aspect of that.
Yes, so I'm using sort of a new word, graphlets, a somewhat different approach to understand graph limits, basically using spectral methods, spectral graph theory. And we know that quite some recent development work on graph limits. It comes from quite a few directions. It's very well described in Latti's book, actually, from the powerful tool regularity lemma by Szemeredi, Cauchy randomness, different equivalent graph properties, which are sort of different matrix for studying graphs, and some classical probability theory about these exchangeable probability measures, and more recently in the studying of so-called complex networks, when the limiting behavior can really revealing its structure. And there are many people working on this area, including a lot of people we know here. So what I'm doing is sort of understand it from the spectral graph theory point of view. When we have a sequence of graphs, what it means converging to a limit. So see, here is beautiful for Blackboard talks, but one advantage of using the VGs is that I can steal slides from Lova's talk. Then I don't have to make all these. So you have a graph, and you have adjacency matrix. And one thing you can do is to replace each one by a little square, little rectangle square here. Then you get normalized, you get 0, 1 by 0, 1, this W matrix. So if you take to the limit, you can see sort of smoothing out if we are lucky, if approaching limit. To get the convergence down, I stole another view graph from Latti. So basically, there's this cut norm, which means you take any subset S, any subset of T, and look at the measuring the difference of two. You allow yourself to relabel and take the norm, this cut norm, called cut distance. Okay. So so there are these work on so-called graphon, which you can use regularity lemma, which you can take any graph, you partition it into finite number of parts, so that whatever between two parts is you can approximate by random with very good approximation. And all the finite many means independent of n and only depending on the epsilon. But the catch here is that it's only good when this error bound is epsilon n squared, which means it's good. It's great for dense graphs. You can sort of get very nice block structure. On the other end of the spectrum, we have very sparse graphs like the cycles. And if you take the W matrix, you can see sort of drifting to 0. So if we just use W to represent these graph limits, all the sparse ones are going to converge to the same thing, which is 0. So you can see it needs different approaches and with a different name, and it's not seeing everything as clearly as the regularity lemma have led us for dense case. So there's sort of a gap in between, and so I'm sort of in the spirit of all these things, create another word, sort of try to attempt to bridge the two. And for general degree sequences by using spectral method. Well, what are graphlets? That's the first question. And the word manifold comes into mind. But I want to say it's indeed, you take continuous things, you can look at these graphs by discretize it, or the other direction, you look at the limit, you get a beautiful surface. But it's definitely not graphlet. It's quite a different behavior structure. See, you have very restrict. So here, roughly an outline to say what graphlet is. Okay, so we are going over convergence in spectral distance. And because of the name, graphlets, sort of in analogy to wavelet, so we have the basis, the geometry, and universal embeddings, and so on. So we started with the Laplace operator. So it is one way to think about it. It's really a normalized form instead of adjacency matrix. Adjacency shows the connection. Two nodes are adjacent, but Laplace operator really look at the rate of changes. So it's scaled slightly differently. And instead of uniform measure of 0, 1, the usual, the best measure, we really choose these exchangeable measure, the mu n, and then take limit. And instead of usual cut distance, we have to normalize it a little bit. But it's basically cut distance, okay? And if we allow all that, the convergence means, to its limit means, well, in the mu norm, it converges. And mu product sort of coming, first of all, the measure has to converge, and we can use that to define the convergence of the Laplace operator. And we also need the degrees, the ratio of the degrees converge. Okay, so when n and m are big enough, they are not so far apart. So after relabeling. So another way of looking at this is we have our Laplace operator, which is dn. So for a usual graph, it's just this is the transition probability matrix for people who are familiar with random walks. And I minus that, so all the spectrons positive. And it's equivalent. If we symmetrize it, then all the eigenvalues are real and so on. And we are going to replace this A by the W operator here. So in a way, it is just scaled by the degrees. So that's basically the difference. Okay. So for people who are more familiar with the more classical kind of Laplace operator, for paths, it's basically the second derivative up to a scale. Yeah. So this Laplace operator for Gn, for a graph in our graph sequence, we basically take the, for each vertex, we can define its measure. So, and extend it to the case of squares, little squares to the W's. And the limit is just taking the limit. Okay.
I'm confused.
Yes.
So could you explain what, so you have, what are you taking the integral over? Or what is the?
Integral is over 0, 1, actually. But here, it's of course, I skip a lot of detailed definitions, which are in the paper on my webpage. But here, it's responding to the little interval corresponding your vertex V. So, okay. one way to think of it is, see, usually when you do integration, you will have a dx, right? I'm replacing that dx by this mu n, which is the measure. See, this sum up to 1, so it's a probability measure.
But
So,
how do you order how do you place the vertices on?
We are going to allow, or it's a exchangeable measure, so it's already allow you choose the best measure when you have 2 together. When you only have 1, then it doesn't matter.
What's an
as much.
exchangeable measure?
Well, it's it really independent of how you order things. So so like a graph, how you label it, you still have the same graph. So it's actually a perfect fit for. It's well studied with quite a bit of literature. Actually, David Aldous have quite a few old papers on this. So it's a very special measure, but it's perfect for this. And that's why there are quite a few papers by people in probability on graph limits as a result. Yeah. And if we truly talk about measures, so there's, anyway, Russell?
So an exchangeable measure is something like, it's a measure where there's an isomorphism that moves every open interval.
Right.
To
You have an equivalence. Right. You allow any measure preserving map, and they are equivalent. I mean, I actually in the writing version I try to put in all that, but here sort of just trying to give you the idea, and I delete the notation allowing you choosing the labels and so on. But in fact, that slice I stole for Lati, which has this measure, so you allow you to, when you have 2 you want to compare, then you allow at least 1 to go over all the labelings, possible measure preserving maps. Okay. So I'm going one step.
I of V is an interval associated with the node V?
Yes, yes. That's the tiny interval. So you can see that relation with the W here. So there is a scale here. And these integrals, I think my previous page has defined, these are just, this going from here to here, you put mu n there, which are just the definition. Okay. So basically, it's a scale version. So when we are talking about cuts, usually it's the edges between a subset and its complement, and it has relation with eigenvalues of the Laplace operator, the Cheeger inequality. If you use this version of delta n, then you can sandwich the eigenvalues with the Cheeger constant of the graph, which is just defined as number of edges in between divided by the volume of the smaller parts. A second notion of a cut, a little bit more general. You have 2 parts, any S and T, and try to estimate the number of edges in between. And there are various discrepancy inequalities for controlling this. The one which we see the most often is like this. The number of edges in between S and T, with one endpoint in S, another in T. Then you take the size of S and T and multiply by the edge density as an estimate. And this is can be bounded above by lambda S and T under this condition. See, this S and T really is the inner product with the O1 function. It is the Fourier coefficient for that eigenfunction if one is an eigenfunction and lambda is the second largest eigenvalue of A. Second largest means absolute value, actually. So, and this inequality is true. So if we have a control of this lambda, then you get a control of the you can estimate the number of edges between S and T pretty globally, just using its size. But as you can see, this will only be very good if one is, the eigenfunction is close to this O1 function, so only good for almost regular graph. And then it works pretty well. But if the graph is not almost regular, we sort of have this generalized version. So instead of adjacency matrix, you normalize it by the degree matrix. And as a consequence, the eigenfunction was normalized with involving degrees. And the Fourier coefficients, when you project to that eigenfunction, give you this volume S, sort of proportional to its degrees. So volume S times volume T over volume G. So for the regular case, it goes back there, almost regular case. So this, for general degree,
you probably should have a delta there too. In front of the volume of S times volume of T.
No, there's no, because it's already hidden here. For regular graph, the delta will immediately coming out of here. So this is delta, like S squared. It's going to cancel out beautifully and leave you with that delta. It come automatically embedded in the two volumes versus one volume. Okay. So in a way, we are doing graphlets is sort of like a third attempt. So instead of estimate this, the number of edges in between the this cut, by sort of expected value of a random graph everywhere, we are trying to compare two graphs or one graph with its limit. So replace this by the limit, which could be much more general and more structural. So we are talking about the discrepancy distance between two graphs, which sort of, if you get down to the right choice, whatever choice of S and T, you are comparing these two. Okay? So I want to say convergence in discrepancy distance is equivalent to convergence in spectral distance. We define the convergence in spectral distance. I want to say convergence in discrepancy distance, which is the normalized Carnot, are really equivalent. So one way to think of it is that the number of edges between S and T, if I use W, it is sort of like this. And here, I actually take the little measure, so I have to put n squared to put it back. Okay.
So if G and H are sparse, couldn't you have, one side?
If
one
it
side
is
could be quite large, and the other side could be
but you normalize, your mu is very small too. So the eigenvalue still controls. So in fact, I want to show you this proof, at least the idea of pole proof. Russell?
So that definition makes sense when G and H have the same dimension, but I
right.
wanted to compare.
Right. I actually wrote this one because it looks friendlier. But the fact is that in general, I'm going to, instead of using an, I'm going to use wn. Then you can still talk about the same thing. Just replace every one by a little square. Okay. Yes? Pardon?
Could you go to the previous slides?
Yeah.
So on the second attempt, is volume S times volume G or times
Volume
volume T?
T. So this is the sum of degrees in S, and this is sum of all the degrees in T, and this is sum of everybody. Oh, sorry, this is T. A typo. Thank you. Should have seen that. Okay. So so you can see that this format, if I write it, use this normalized form and mu n, is really the same thing. But the only difference is I choose this form and generalize it. Okay, so
Sorry, what is the spectral distance?
the spectral distance is, I'm taking, okay, this previously the spectral distance, I think here. This is the how you define the spectral norm. Okay, so it's basically just take the mu norm, take limit of this, take limit of this. Sorry about that.
Define the spectral norm again.
I'm just taking delta n and delta m and use their w's instead of an's, and take the mu norm. The mu norm, you define the mu inner product when you have a function, comma, another function inner product mu. It's just you take integration over 0, 1, which I use as labels really, of f and u, and put the mu n in between to put them together. The measure would be, instead of usual best measure, we are using exchangeable measure. And it depending on the degree sequence.
Okay, but
Okay.
for fixed finite graphs,
Yes.
are you like looking at the difference between the weighted adjacency matrices and then taking the largest eigenvalue of that?
Yes, spectral norm. So both of them, when they have the same dimension, it's easier to see. Yes. You just take difference. But if they are not the same dimension, you use their W form, and you still can take difference. Okay. So where am I? Okay. Right. Well, I'm actually, so I'm really go back too much. Right. This inner product, which is what I was talking about. The measure is, it's a measure. I think I'm backtracking, confuse everybody here. Okay, my 3 attempts, right? I'm about to hit the interesting part is the graph limit part, right? So one direction, the eigenvalue implies the discrepancy distance is the easy direction. The other direction, you need a fact, which is actually not too hard to prove. So if your matrix is a difference of the two things, and both of them sort of behave pretty good, then you can go back, suffering only a log factor. So if this is a discrete form, which is well bounded, then the continuous form, which will give you the eigenvalue bound with a small constant difference. So this probably answers David's question. So you can go as long as the cut distance is good, then you get your spectral bound there as well. So.
Question: is that kind of related to this linear work of a linear limit student?
Yes. They were indeed. It was in that spirit. But that one is more like the attempt 1 to do the inverse. Yeah. Here is the more general form. Okay. And then I'll try to give you an idea of a few other things I sort of put together about which actually was the motivation for me to get into graph limit. See, at the beginning, we really try to understand random-like behavior of a graph, right? So the eigenvalues is very well studied. So if we do this form of eigenvalues. For random graphs, G and P, there's a lot of work trying to understand its eigenvalue. And it has this sort of semicircle law here. So what happened to the limiting behavior if I look at it like this? This paper with Ron Graham and Richard Wilson. We study these, if we have a sequence going to a limit, it's quasi-random if, so all these properties are equivalent, all but one eigenvalue are little o n. So the first eigenvalue is n over 2 for edge density a half. And there are more properties. This is equivalent to the case that any pair of nodes have co-degree n over 4, which is sort of a reasonable thing. And any subsets induce about the right number of edges. Or between two subsets, you have the right number of edges. So number of 4 cycle count is right. And in fact, any graph H with fixed, like Peterson graph, for example, the number of occurrence of H in G is about right. Okay? So these, some properties are much more than others. For example, like this seems to be stronger, and this seems to be stronger, but anyway, they are equivalent. So if I write it in graph limits language, this means it converges in a spectral distance. And this means it converges, the sequence converges in C4 distance. It's actually sort of like this one, right? This is the cut distance. And this is, it converges in sort of, this is really a trace distance. See, the trace usually is bigger than the eigenvalue, but for dense graphs, it's turned out to be the same. So all the accumulation of other little eigenvalues didn't even make any difference. That doesn't accumulate. See, this is sum of all the fourth power of eigenvalues. They all drop off, just the main one is the dominating term. And so this is the subgraph count measure. So quasi-random really say all these ways to measure randomness are the same, but only for edge density a half. What about for general degree distribution? So if I have expected degree Wi, and I define this probability accordingly for every pair, I flip a coin, okay? For example, Erdős-Rey model is the case, or the Wi, all these weights are the same, okay? Then what happened is the graph limit. See, all this part we spend so much time struggle with just vanish. It's one dimensional. So we struggle long and hard to write sparse quasi-random paper. And after I learned about graph limit, then all of a sudden it was very clean and clear. Got rid of a lot of nasty conditions for sparse quasi-random because the limit is just rank 1. And this I minus delta only has one eigenvalue, 1, and all the others are 0. So all the epsilons we previously worried so much about all turn into 0, see? So, and this, another way to say it is only its projection on this main eigenfunction matters. So this is more familiar. This one is the cut norm, generalized cut norm, okay? So this is the expected value for close to randomness. And it's generalized very easily to all general graphs with any given degree distribution. But of course, among this list, what was unsaid is about subgraph count, which in fact is quite a bit interesting work. Even, you know, that if you contain C4 the right number of times, and you force Peterson graph among all other graphs to be contained the right number of times. So the subgraph count is sort of, well, combinatorics is an important property. So what happened to it when we go to general degree distribution? See, if your graph is very sparse, the problem, so for example, the edge density is like in this range, so you have about n to the 3 halves edges instead of n squared, okay? in that case, you probably will get very few C4s. And in fact, in this range, you hardly get any C4s. Very low order of C4. The error bound is huge. So instead of C4s in our earlier sparse quasi-random graph, we started to consider C2K. And there are a set of difficulties in dealing with C2K, especially for general degree distribution. So what K is this C2K forcing containment of large family of other graphs? And one thing we know is that if the number of the number of currents of C2K in Gn is much larger. See, this is the case you just, your C4 collapse. You really walking around in the backtrack and stuff. It has to be bigger than this to make sense. Otherwise, the C4 is not the real structure there. Okay? The dominating term are those collapsed ones. So it has to be bigger for it to make sense. But if this is indeed sufficient, if you plug into such a condition, then the 2K will be enough.
What's P sub K plus 1?
This PK is the path on K plus 1.
Path of
Point.
length K plus
So if you see this, for every pass, you can unfold it and make it the double full cycle. Every edge appear twice. So this definitely should be much more than that in order for this to make sense. So I'm leaving it. And as a supporting evidence for dense graphs, definitely this is true. Either using second moment method in the quasi-random graph or use regularity lemma in the paper of Lovas, Shosh, and Mickey. Okay. So, and then instead of rank 1, we natural setup for rank 2, which actually makes sense for complex networks because you want to separate the community into, if you know the limit is split into 2 clusters, okay? So then the generalization is very easy because I just have 2 eigenvalues instead of just 1. And all the others go to 0. And another way to say it is that it's basically your measure split into 2. It's a combination of 2. And your graph split into 2. So instead of just random, just have 1 term. And here you get two terms for the canons. And it takes actually a little bit more work than I first anticipated. I thought with this great format as graph limit, 2 should go through. But that was in the detail, right? And rank K is much more complicated. And, but for dense graphs, it's beautiful by using regularity lemma. You can write out the basis very nicely, sort of borrow from the block form and fix up the rest, these local ones, pretty nicely. And for very sparse ones, see a lot of manifold, you discretize it. It is well defined with Laplace operator and with their eigenvalues. And in fact, you have more eigenvalues than before. And you can just pick those you like. Then you get the basis for Cn. And in the remaining time, I'll just give you a little bit, really, only 5 minutes. Okay, so for the gradient operator,
Sorry, may I ask how you define the graphlet? Are they subgraphs or are they just a sequence of graphs? Can you explain? I mean, what is graphlet?
I actually defined as a pair. It both as the omega, which is the surface itself, like a manifold, and the operator on it. So it is a pair. And in fact, if you are really particularly about it, the omega, the graph limit there, come with the measure. Yeah.
So it's a limit of your sequence?
Yes, yes. It defined as the limit of your sequence.
Is there a particular reason that you use the lit because it reminds people of the name of wavelet?
Yes, because I think I want to make sure it's a little bit different from the previous definitions. And graphlets is, it does have this analogy with wavelets because it all starts with the operator. So the eigenvalue and orthogonal basis make sense there.
But graphlets are not basis of graph. You span your graph. Is that something like the basis that you can span your graph?
It is the eigenfunctions of your surface. So to me, that's how I leave it. Yes. Because delta is well defined. The Laplace operators will define on the omega and its eigenvalues. So for example, for Cauchy random graphs, it was the simple case that the graphlets just have one vector or ones. Yes?
Can you give us, so like you were mentioning the cycles, that should be like a simple case.
Yes, it is.
So what happens when you take the limit of the cycle? What kind of?
Then you are going to get very smooth one cycle. And of course, one thing I want to point out, suppose you take the grid graph, which is a product of two cycles, the Cartesian product of two cycles, then that shows the usual measure of 0, 1 doesn't quite work. But the mu measure works because the mu measure has two directions.
Sorry, so what do you
The
get
graph
for
measure.
the-
Then
what's the limit
if
of
it's
the-
a grid, then you'll get beautiful grid.
So it'll look like a grid.
Right,
But
right.
it's an infinite grid.
Yes. So your gradient operator, in fact, I have my picture here. See, for a grid, you have directions. So it's not like manifold. At each point, you have a tangent space. Here, I have a frame, but the frame is not a basis of a vector space. It tells you the direction you can go. And the direction comes also defined by the limit of your graph
So
sequence.
is the limit the infinite grid, or is the limit this continuous square?
It's a continuous square.
Okay.
It is
But
the
is it-
tangent, but only allowed in those four directions.
So, but it's got it's a square, but not with the standard.
It is like this. It's if you like to think of it as a manifold, then it is just a square, and at each point there are four directions, which are the limit of those four directions in a sequence. Okay. So basically, this is well defined for dense and sparse graphs. It's just the rate of change in particular direction after you take a small step, right? Limit means take a small step, and take smaller and smaller steps means you take bigger and bigger n. So this n is actually giving you the scale of taking the limit. Then, of course, the difference, like what Russell said, that this discrete frame has restricted directions, among many other things. Your geodesics, you can only live in those directions for your gradients.
So for your example of grid graph, the graphlets in the limit will be the Fourier modes.
It will be smooth, just a square.
So periodic
Okay.
boundary condition.
Yes. If it is cycle, then if it's path, then it's not. You don't identify the boundary. But if it's cycle, then you do. Yeah.
So in that case, the analogous to a Laplacian operator on a periodic Q, it will be the eigenfunctions will be Fourier functions, and that would be the limit of the graphlets.
Yeah, that's correct. And remaining couple minutes talking about embeddings. See, in the geometry, in the differential geometry direction, they are work of comparing two manifolds. And what they usually do, many different ones, what they do is to embedded in a universal space, in some Hilbert space. And that's the way to compare two manifolds. There are work of Gromov and many others, Benson, Barad, and among others. So in fact, what I'm using is the discrete version of that. And, but of course, this discrete version I used before. So that's sort of a natural ways to think of it. So what is this space? So there's one notion you have to preserve distance to some extent. But if your graph are small world graphs, means any two nodes are pretty close, then we sort of have finer kind of quantifying, which I'm not going to get too much into, sort of page rank kind of thing. And we want to preserve cuts, so sort of two directions. So one way to do this is use the He kernel. So He kernel HT, this operator satisfies these He equations, but one way to think of it is just an exponential sum of random walks. And if you look at the transform, all these eigenvalues are very nice, okay? Sort of exponential form and with the projection to the eigenspace. And if we use this, then you can check that indeed all these entries are very nice, and in fact, sort of like serving like a probability when you fix one point. So like a probability measure. And I'm going to use that as assigning each vertex a vector if it is a finite graph, okay? So it is really mapping each vertex like this coordinate in higher dimension space, pretty high really, too high, okay? But the nice thing about this T, this temperature T here, is that that's a parameter allows you to choose it, most of your weight, you can choose it, localize it, okay? So it doesn't spread as much if you choose the right T. So you can, so suppose you have a subset with a small Cheeger ratio. So it is sort of like a cluster, not too many edges leaving. Then it takes a proof. The He kernel satisfied if you have a seed from sort of a probability, choose a random point in your cluster, then the weight will pretty concentrate within that set. And this really means most of the points, the majority of the points actually, you can control this ratio, spread weights within that cluster pretty good. And can use this to do partitioning, local partition algorithms in the following sense, sort of a Cheeger-like inequalities. So all you need to know is you order all your vertices according to so this is a vector, right? You choose a point randomly, okay? Hopefully in your subset T. Then you order all your vertices according to this function. And you grab those which within the range you are interested in. And the best cut there is this chi-square, which will be related with this Cheeger ratio, which is theoretically could be the optimal. So sort of a Cheeger-like inequalities. And all you have to do is to do sweeps over a random point, okay? So previously, I actually have this exponential form of page rank by using H and have local partition algorithms. But by rewriting it for graph limit, the proof actually simplifies. So,
but
yeah.
page rank, what do you mean? Like order in eigenfunction? Or what?
really, it's organization of random walks. It's a modified version of random walks.
Yeah.
So instead of you say you take one step, you take two steps, takes t steps, log steps, or log plus one steps, you take a sum. You combine them with a sum. But the way to combine them using that t.
And then the hitting probability of the node.
Right. And use that measure to take your random walk steps, basically. That's one way to say it. But there's a lot about PageRank stuff. In fact, I will talk about it a little bit more later on at my graph gauge theory talk in the math department. So that PageRank sort of sneak in over there as well. So with this said, I just want to say that there is a draft ready in my webpage, but I was hoping being here can get experts' comments. So I'm pretty sure I will revise it in the next couple of days. So okay, so that's about all I want to say.